Distinguished guests, good morning. Today, I will share with you the journey of our efforts with large time series models over the past 2 years. As we know, time series data is a very important industrial asset and a fundamental element. Dean Wang mentioned the transition from theory to application, which is actually a kind of chemical transformation. In this process, large time series models are needed as a fundamental component to enable this kind of empowerment. In time series data analysis, we often talk about descriptive analysis, which is a review of the past, and predictive analysis, which is a forward-looking outlook on the future. This is especially true when it comes to making forward-looking predictions about the various complex operating conditions of our machinery and equipment, ultimately achieving intelligent operation and maintenance. So when it comes to time series training data, people often hear about things like weather forecasting, or more recently, quantitative trading, and so on. These fields have actually been very successful. In fact, in the industrial sector, the analysis of time series data has an even longer history and even more success stories. It's just that it hasn't been put under the spotlight of large models, so people tend to hear less about it. So today, let me share with you the main challenges in time series data analysis. The first challenge is dealing with the non-linearity in the changes of time series data. As everyone knows, the core feature of deep learning technology is its ability to model non-linear patterns. Time series data often changes in a non-linear way. However, the mathematical tools people commonly used in the past, such as ARIMA, whole winters, which are typically used for linear modeling, meaning they model the correlation between a certain point in time and previous points using a linear approach. With such models, theoretically, they simply cannot perform non-linear modeling. The second issue, which is discussed even more often, and which Jalin also mentioned earlier, is the non-stationarity in the changes of time series data. This actually refers to the fact that the sequence keeps changing over time and is hard to predict. For example, as Jalin just mentioned, maybe today the equipment is unhappy, right? Tomorrow, its operating condition might change. In such cases, it's very difficult for us to consider the problem from a relatively steady or stationary perspective. So how is this traditionally handled? To deal with this kind of complexity, we often have to address each situation individually. We design a lot of rules and discuss each scenario separately. So, in response to this, our team actually started about 5 years ago by focusing on deep learning techniques for time series. Starting from the initial pre-processing of time series data to building deep learning models and finally developing large-scale time series models. A very important and crucial point here to consider is that behind a large and complex model, there are actually many fundamental and essential elements, such as basic operators and core components that are vital for its functionality. For example, the well-known frequency transformations like FFT, as well as decomposition and planning, are all fundamental operators in time series data analysis. Their implementation is crucial for building a large-scale time series model. This is extremely important. This is the roadmap for time series analysis models, and I believe it is widely used by the mainstream. Statistical models, for example, are still widely used. Just like Dean Wang mentioned earlier about 1.0, 2.0, and 3.0, we believe the same progression applies to time series data analysis. Traditional statistical analysis represents 1.0, deep learning models are 2.0, and large time series models are 3.0. There has been a significant evolution through these stages, and our team started out in this field very early on. Our important starting point was serving the Beijing Winter Olympics. Our goal for developing the first generation of time series infrastructure was to ensure it was practical, effective, and reliable for use at the Winter Olympics. This was a great starting point and really showcased our team's commitment, as Professor Sun mentioned, to creating software that is usable, useful, and reliable. I often tell our students the same thing. To build time series models that are usable, reliable, and effective. Starting from this foundation, we actually experimented with every technology you could think of. People might ask whether time series problems can be tackled with recurrent neural networks, convolutional neural networks, graph neural networks, or transformers, and so on. I believe these are questions everyone would ask. So rest assured, we've explored all these technical approaches for you, figuring out which ones work and which ones don't. So, moving into 2024, or rather, the second half of 2023, at the last IoTDB Summit, what we actually released was the AI node. When we launched the AI node, it natively supported our 2.0 deep learning models. However, at that time, we were already working on transitioning from deep learning models to large models. So why are we doing this? Actually, as Jalin just mentioned, there's a very important reason. Without large models, this technology isn't very user-friendly. It's hard to use right out of the box. It's difficult to achieve one-click fine-tuning. Even if I use a deep learning model, I might still need to go through the entire training process from scratch. It's just not easy to use, and that's a key reason why we're developing this large time series model. The driving force really comes from our users' needs. So what about 2024? As you can see, the development of large time series models is happening extremely fast. It may already be a trending term, but in fact, its history, or rather its emergence, is not even 2 years old yet. This really shows how quickly the technology is advancing. There's a word Chinese often use, which means to compete fiercely, right? This kind of competition is actually the driving force behind the rapid development of this technology. Whenever I teach deep learning at Tsinghua, as soon as I talk about convolutional neural networks, I always tell my students, let's roll up our sleeves and get to work. After all, convolution is about building a machine that knows how to roll or convolve. That always gets a knowing smile from everyone, as if to say, yes, this is exactly how it should be done. All right, next we'll discuss the 3 most fundamental motivations behind the development of large models. The first motivation is actually data scarcity. People often talk about how to make the most of big data. In fact, there's a very classic chart in the field of big data and deep learning that shows the relationship between data volume and model performance. You'll often find that when the amount of data is relatively small, using traditional statistical methods like ARIMA and so on actually yields pretty good results. At this point, should we be content with modest gains, or is this still not enough? I believe the answer is the latter. It's not enough. As our data scale grows larger, we find that machine learning models like light GBM start to come into focus. I believe these are also technologies that are very commonly used in everyone's toolkit. However, when you notice that the scale of your data increases even further, light GBM and some statistical models have an upper limit in terms of capacity. This is just like what Dean Wang mentioned earlier about parameter scale. It's similar to the human brain. When my data volume is extremely large, the number of neurons I have must also be sufficient. Otherwise, I'll hit an upper limit, a bottleneck. From this, it becomes clear that we need to explore this issue. At the end of 2023, we discovered this phenomenon. We found that previous models would easily reach saturation. Once the data reached a certain scale, their performance could no longer improve. This is actually what led us to explore the scaling law and further study the motivation behind large models. So, this is the entire process we reported earlier. We hope that large models will have the ability to learn from large-scale data and then empower multiple downstream tasks. In other words, to possess a one-to-many capability. Or as we call it, one repository, one model. We say that a single database can support many applications, but a single model can only support one application. This situation definitely needs to change. Otherwise, we believe that it will be difficult for machine learning technology to become a foundational infrastructure like databases. In this process, we were among the earliest teams internationally to work on large time series models. However, in this field, several major companies are also working on it. We found that although the time spent has been short, it actually reflects something. That is the difficulty of technological exploration at the very beginning. Actually, no one really knew how to build large time series models. What was everyone's most natural idea? To replicate the success of language models, right? Even now, such work continues to emerge one after another. Similarly, in this diagram, we can see that each team's exploration is actually addressing just a small problem within the field of time series data analysis. Later, you'll see that time series data analysis is actually more complex than natural language analysis. For example, Google developed a model that segments the sequence into windows and then applies attention modeling to different windows just to solve this one issue. But actually, this is something that language models do all the time, right? Now, if we look at Salesforce's Moirai model, it tries to do multivariate modeling. But how does it actually do that? They flatten it, right? They take multiple variables and flatten them into a single sequence. I believe none of you here would agree that this approach is truly viable. Of course, doing this does bring some improvement. You'll observe a delta. This means that multivariate analysis is definitely necessary for time series, but what is the right way to do it? That still isn't particularly clear. There have also been explorations of other models, with perhaps the most well-known being Amazon's Chronos. It's a typical example of using language models for large-scale time series modeling. So, what's the issue with this? We've actually communicated with their team, and currently, the mainstream support for this model is to predict 100 points. That is, the next 100 points. Because as the prediction length increases, the model's resource consumption becomes extremely high. Why do you think that is? Because it treats each time point in a time series as a word in natural language, right? By doing this, the length you can handle becomes quite limited. And there is one even more important reason. Each word in natural language carries semantic meaning. Does a single point in a time series really have enough semantic meaning? As everyone knows, in the field of time series, the window is probably more important. In other words, how a token is defined may not be such a simple matter. Of course, later on, people explored all kinds of approaches, including using mixture of experts models to make the model parameters even larger. In fact, we are currently collaborating with the ByteDance team. So why are we collaborating? The reason is that even with the mixture of experts model, there are still many bottlenecks. This slide reviews the main areas of exploration in large models over the past year and a half. Next, let's address why this exploration process has been so challenging for everyone. It actually comes back to our data. In fact, all of you here are experts in data and have a deep understanding of its characteristics. But for those of us working on models, what we often overlook at the beginning is the data itself, because we jump straight into using transformers. We believe that transformers are the golden rule, the first law in the field of deep learning. We want to achieve good results right from the start, but we often ignore the characteristics of the data. Time series data differs from natural language data in two main ways. First, natural language is a single sequence, while time series is a multivariate sequence. Second, the diversity of time series is much greater than that of natural language. A word usually has only a few meanings at most, right? But a sequence can vary in its shape over time, its sampling frequency may differ, and the distribution of its value range can also be different. In the deep learning era, this is called OOD, or out of distribution. It's very easy for such out of distribution situations to occur, which makes it impossible for the model to handle them effectively. So based on this, with our Timer 1.0, we focused on solving two main problems. The first problem is that we manage the data set. This management includes normalizing the data, standardizing the range of its values, and also using some important statistical tests for time series data, such as tests for non-stationarity and periodicity. There are many indicators, like the ADF test. Through these tests, what do we do with the data? We process and manage the data to create a training data set suitable for large models. This is something everyone heard a lot, right? In the field of language models, everyone is always working with data, always managing data, and it's the same in the time series field. If we directly use the data collected from our production environment for training, the model is very likely to perform poorly. Just think about the simplest scenario. For example, if a certain data point is missing, or if a particular value is extremely large, just think about that. When a value is extremely large, it can exceed the model's numerical precision limit, causing the model to fail. This shows just how important it is to normalize heterogeneous data. Our exploration at the time proved that only through proper data management could we successfully train this large model. Let me add a bit more here. At that time, the model we used was a so-called you can see that it was a so-called pure decoder architecture, decoder only. This is also the architecture used by all current language models. Let me share a little anecdote with you here. Actually, during this exploration, many teams used what's called an encoder-only architecture, meaning a pure encoder architecture. Why is that? It's because encoder architectures are easier to train. Even if there are some minor issues in your data, the model can still be trained. However, its scalability is always limited. This shows that if we obtain a relatively good large data set through data governance, we can train a large model with a decoder architecture. So what are the benefits of this? We found that it can handle both prediction and completion tasks, as well as anomaly detection tasks. This is what supports the multitasking capability of large models. This capability is often quite difficult to support in encoder architectures. This also demonstrates that our Timer 1.0 has a relatively strong generalization ability with small samples. It only requires a very small amount of data for fine-tuning or for making adjustments to the model, and it can achieve quite good results. Moreover, we have observed the so-called scaling law. As the parameter size increases, the performance improves, and then the duration also has a positive effect on performance. This is the multitask adaptation capability we discussed earlier. So what did we discover with Timer 2.0? We found that in the field of time series, there are actually a large number of variables that can have a significant impact on the target variable's performance. And in fact, when building this model, how to model the contextual relationships between variables and the contribution of different variables to the target variable is actually very crucial. So in this process, we also upgraded this technical approach. The most straightforward method, as we mentioned earlier, is to treat different variables as a sequence. This approach faces two problems. First, the sequence becomes extremely long, making it impossible to train. Second, the temporal order is lost. This is something that Professor Wang has especially emphasized to us over the past year. For time series, the most important aspect is time, right? When we split multiple variables into a single variable, the temporal order of that variable is naturally lost. This actually presents a significant challenge. From this, we realize that time series data is essentially two-dimensional data. Time is one dimension, and variables are another dimension. This means that the attention mechanism in large models must also be two-dimensional. The attention mechanism along the time dimension models the relationships between the past and future in time, while the attention mechanism along the variable dimension models the correlations among different variables. This probably reminds everyone of a classic model called VAR. That is the vector autoregression model, right? But compared to VR, what are the advantages of this model? All of its correlations, including temporal correlations and variable correlations, are modeled through the attention mechanism. In this way, it can capture adaptive correlations rather than correlations with fixed parameters over time. This is also why the transformer model's most fundamental advantage over traditional models is the adaptiveness of its attention mechanism. In this work, we discovered an important feature which is shown in the top left corner of this figure. Previously, when working on tasks, people often found that if you consider too much historical data, the performance actually decreases, right? Why is that? Because when you look too far back in history, you might introduce some irrelevant information into the prediction, which leads to worse results. However, after we applied the adaptive two-dimensional attention mechanism I just mentioned, the longer the historical time considered, the better the results tend to be. This lays the foundation for making full use of historical data, allowing us to leverage long-term historical information for this task, rather than being limited to only the most recent or popular data. This is actually very important for large models. Alright, with Timer 2.0, we have also consistently ranked at the top in various international evaluations of large-scale time series models. Next, let's focus on Timer 3.0. Timer 3.0 actually addresses a question that often confuses people. When I am given a time series, is its future determined or uncertain? In reality, it actually has a considerable degree of uncertainty. At this point, if we build a model that is completely deterministic, then for a similar input sequence, the predictions it gives will also be similar. However, in the field of time series modeling, there's often what people refer to as, for example, the chaos theory, where a small change in the input sequence can actually lead to a large change in the output sequence, right? So to have this kind of capability, the model must be a generative model, one that inherently has the ability to generate those sequences that are most likely to occur in the future. So, as we all know, language models are essentially generative models. Otherwise, if it only gave a single deterministic result for every input, then many problems simply couldn't be solved. The powerful reasoning abilities we see today are actually built upon this generative capability. If you think about how we humans solve real-world problems, we often imagine many possible paths, then search and test among them repeatedly to find the correct one. This means that the model should have the ability to generate the most likely hypotheses, that is, to generate assumptions and then verify them. It also means that for a time series of data, it should be able to generate all the most likely future developments and then further evaluate them. Alright, so in this process, as we reflected on our past technical approaches, in a sense, aside from inheriting the technical paths of Timer 1.0 and 2.0, we actually overturned some other technical routes. Other technical routes include modeling time series by discretizing them, turning them into words or discrete tokens. We found that this process leads to significant loss of accuracy. There are also some issues with generalization ability, some problems with generalization, so we still chose to use a continuous modeling approach, utilizing the attention mechanism and decoder architecture developed in our Timer 1.0 and 2.0. In this process, when building Timer 3.0, we applied first principles from the field of time series analysis. That is, the basic principle of ARIMA. There is now a general consensus that when predicting a sequence, it should be influenced by the previous time points. On this basis, a series of different orders of noise will make corrections to the prediction result and finally produce the outcome. This is the fundamental principle behind the classic autoregressive and moving average models. So, we take this kind of first principle approach and fully implement it with deep learning, resulting in an equivalent deep learning realization. The difference is that it has the ability to model non-linearity. Here, the transformer architecture on the left side serves as the decoder for autoregressive modeling. On the right, we use a generative approach, a flow model, to perform generative modeling so that the effects of different noises on the prediction results are incorporated in a nonlinear way. This leads to the development of the Timer 3.0 model. So Timer 3.0 has the following features. First, it can perform generative prediction, meaning it can output multiple results for a single input. Second, it is a time series native transformer. It does not use certain discretization techniques from language models that result in precision loss. Third, it is the first to be trained on trillion-level data points. That is, trained on a data set with a trillion data points. Let me add a bit more here. Collecting this trillion-level data set actually took us a year and a half. This shows just how valuable data is as an asset. So, at our innovation conference today, how will we innovate in the future? At the data and model level, we may need to achieve a synergy where 1 plus 1 is greater than 2. When we deploy our IoTDB onto our partners' production lines, we can use the data from those lines to further customize our own large models. The upper limit of these large models will be higher than what we could achieve by training only on the data we've collected ourselves. It will definitely be much higher. This is one of our fundamental beliefs. Alright, these are some of the results from this model. You can see that it is capable of producing some pretty good in-depth prediction outcomes. Now, with these results, there's actually a lot of room for imagination. Some of you might wonder, if the model generates multiple results for a single sequence, which one should I choose, right? Actually, there are solutions to this problem. As long as the model has generative capabilities, we only need to do a little bit of human alignment, and it can very effectively select the result that humans prefer. This has been the key to the success of large language models in mathematical reasoning over the past 2 years. They generate many solutions, right? Then, with a bit of human adjustment and alignment, the correct answer can be identified. But if the model can't even generate the correct solution, then it definitely won't work in the future. In other words, for example, if we use a deterministic model that only predicts one result, and that result is wrong, then there's nothing we can do. But for a generative model, I can predict multiple results, and if some of them are correct, then we can further reason and enhance this process. This is what truly brings the soul of large models into sequential large models. So, to sum it up in one sentence, simply transplanting language model technology into sequential large models definitely won't work. Its fundamental architecture and the governance of its datasets are different. Everything will change, including the core principle of our time series foundation models, which is ARIMA, not the next token prediction used in language models, right? This is a very fundamental difference, and on this basis, we consider incorporating reasoning capabilities, and this is the right path forward. These are also some of our benchmarking results. In the time series field, very classic libraries like Time Series Library, which is currently the most widely used library, and internationally recognized models like GIFT Evo, which is probably the largest time series large model, have all achieved very good results on our platform. At the same time, we uphold the advantages of IoT, which is speed. Our model is extremely fast. Under the same conditions, its inference time is only 1/20th of Cronus, making it probably the fastest time series large model. These are more of our benchmarking results. The results shown in these rankings for our peers are actually those they have publicly released and tested themselves. We simply report their data directly, and then we test and report our own results accordingly. Alright, so this is our report on the 1.0, 2.0, and 3.0 versions of our time series large model. In this process, we are actually paying tribute to GPTs 1.0, 2.0, and 3.0. We believe that the era of Time Series Foundation Model 4.0 has yet to begin. Although the road ahead is long, as long as we keep moving forward, we will eventually arrive. We believe that with the joint efforts of our entire IoTDB community, we will usher in the era of Time Series Foundation Model 3.5 and 4.0. This is what we call the model name card for our model. In large models, there is often something called a model card, which serves as its business card. For different models, what exactly is their profile, how many parameters do they have, how much data, what capabilities, and so on. This is a business card. Currently, Timer 3.0 has achieved this. No blind spots, no weaknesses, and continuous prediction, right? It supports predictions with different sliding windows, parameter scales, including uncertainty prediction, and so on. It has already become a fully powered model. This is the recommended configuration needed for this model. If you want to train a Timer 3.0 large model, we recommend using 4 A100 graphics cards. If you only need to fine-tune this large model, you only need a single 4090 graphics card. This card currently costs about 5,000 yuan, I think. It's relatively cheap. If you only need to do inference, a CPU is enough. I believe our dean mentioned MIT's perspective earlier, right? Currently, GPUs are the main source of computing power, but during the digitalization process, many people might not have GPUs yet. On one hand, we will speed up the purchase of GPUs, but on the other hand, we also need to support the traditional approach as well. All right, so earlier I was maybe a bit long-winded, but I shared with everyone the process of developing time series large models from a more technical perspective. We believe that with the joint efforts of the ecosystem and community in the future, we will definitely be able to achieve even better results with time series foundation models. Most importantly, as academician Sun said, we need to make sure they are truly usable. And not just usable, but used well. At present, we still have some shortcomings and gaps, and we need to keep working hard. Thank you, everyone.